Okay. Please settle down. So this code is again made available to you. It's called array passing 1.f90. So there's a bug in the code. So what it does is so it has a subroutine called set vals. Let's look at the subroutine, line number 21 onwards. Set vals takes an argument a. Now a is a type in out, so it is modified as well in the subroutine. It is actually an array of size 3. So what is happening inside the subroutine is that all the elements of a from 1 to 3 are set to a value of 5.0. And when we use the subroutine outside, when we call it, we are calling it on an x which is simply just one real number. Now if we had used this code many years ago, the compiler would not have thrown an error. Now actually if I tried yesterday, even last year it was throwing an error, G Fortran, but a few years ago it used to compile the code. So I want to discuss the underlying idea here, which is linked to the idea of memory locations, how information is stored in the memory. Even though the code will not run now with the compiler figures out there's a problem with the code, there's a bug with the code, there's a bug in the code, but let's discuss why it used to run earlier in the light of how information is stored in a computer. So when you call it on x, now x is a variable which is equal to 1.0 to start with. So you are passing just one real number, which is 8 bytes, but the subroutine modifies 3 real numbers, 3 contiguous real numbers, which is 24 bytes. Okay. So let me actually just to give you an idea. So you have so I'll break it into 3 chunks. Each chunk is 8 bytes big. This is 8 bytes. Okay, each. So it is 24 bytes that the array A is supposed to have. So when you pass in x, when you pass in the thing, then you pass an x. So what it does is it makes the first chunk, the 8 bytes, equal to 5.0. Okay, that's a 8 byte real number. So x becomes 5.0. But then it tries to modify a memory location which is next to where x was. So what's happening is that you have declared x and y here, which are both real numbers. So x and y in the memory are stored like this. And then you have integers I and j. Now integers by default are 4 bytes each. So the way they are sitting is 4 bytes of I and then 4 bytes of j. So these 2 chunks are 8 bytes and this chunk is also 8 byte. So this is how the variables are sitting in the memory. Now when the subroutine calls, it tries to make x is the first 24 bytes. So 8 bytes it sets to 5, so x becomes 5. Now it tries to access the second chunk, which is the second chunk where y is sitting. So y actually also becomes 5. And then the third chunk, which is actually I and j both together, making 8 bytes. But ultimately the way computer works is it makes things 0 or 1. So 8 bytes is 64 bits. Each bit can be a 0 or a 1. And you remember that we are using IEEE 754 standard here. So that takes 11 bits for exponent and 53 bits for mantissa, 52 bits for mantissa and 1 bit for sign, plus or a minus. So it basically flips the bits to 0 or 1. So depending on how 5 would look in an 8 byte notation, it sets those 8 bytes or 64 bits. Now the first 32 will be taken by I, the next 32 will be taken by j. So whatever those 32 bits represent for an integer, that will be I and that will be j. So what happened was that here you ended up messing y, I and j as well, although you didn't expect that. And the problem was that you passed x into the subroutine where it was expecting an array. And this is very much possible. Sometimes we end up passing an array which is of a different size. So this is what used to happen. Now the code is available. If you try to run it, it throws an error. If you try to compile it, it throws an error saying that there is some problem with the size that was expected. But I want to discuss this because it may happen that you may use a compiler which will work out. So passing things which are not the same size can have issues. It may modify something else and you will have no idea why that is happening. By the way, errors typically are three types. One is a compiled time error, where you have an error in the code, you try to compile it, compiler throws an error, which is the best thing because it won't even execute because it's a compile time error. The other is it runs, it compiles. So you get an executable, a.out is prepared, a.out is available, but if you try to run it, it throws an error. It's called a runtime error. The error happened during runtime, so you know something, there's some problem, but the compiler could not pick it up, you have to pick it up yourself. The third is, it does not throw an error during runtime also. You get a result and the result is not what you expect. That's the worst kind, where you're getting a number but that is not what you expect. So this can actually go into the third case, where y, I and j will have been modified and you have no idea why that has happened. Okay. So this happens because whenever you pass an array into a subroutine or a function that is passed by address. Okay. So this array A, which had 8 times 3 bytes in it, it has an address, like we had this 3401, which is the address of the memory location where that number is sitting, the first location. So whenever you pass it, it passes an address and then it tries to move around with that address. So it goes 8 bytes forward, 16 byte forward and so on. So things are passed whenever you pass as addresses and then address of the memory location, and then the code will do whatever it is trying to do. Okay, so in this case it ended up missing all the variables. So A here will refer to the first location of the memory where the bits are stored, and then it moves forward a few bytes depending on which element of A you're trying to access. So the result is x and y are 5 each, but I and j are something depending on what the bits represent. Now there is another code, array passing 2.f90, which has a bug in it. Compiler will catch it again, I think, as well. So here what you're doing is, you're trying to set 1,000 elements. So A is, instead of 3 A's of size 1,000, and you're passing again x into it. So this time what may happen is it will compile, but runtime will say segmentation fault. This is a runtime error. It's a very standard error that we're trying to get. So this segmentation fault basically refers to the fact that you are trying to access a memory location that you were not allowed to use. So whenever you compile a code, you're telling the compiler that you will be using this much memory, roughly. So whenever you run the code, then it will book some amount of memory in the RAM. So that memory is available for the variables to be allocated to during the runtime. Now if you try to access more than what is booked in the code, so when you say more, what does that mean? That means that let's say you booked some chunk. Again, memory is linear, remember. So you book a chunk of memory. Now you're trying to access, earlier we were trying to access a memory which we did not want to, but that was still booked for us. But now you're trying to access something beyond that. And beyond that, this memory could have been used by some other program. Many programs are running in the computer. You could be using PowerPoint, for example. So the system, the operating system has to be careful that if your program has some memory available to you and you try to use something beyond that, that should not be allowed. Otherwise, you may end up changing something that PowerPoint was using and you may mess up something big time. Okay, so the OS will take care of that. So in that case, you get a segmentation fault. Segmentation fault basically will typically mean that you're trying to access a memory location that was not available to you. Okay. So debugging these faults can be difficult. Those who come from a programming background. Is anyone who has worked in a company for coding job earlier? Was actually gotten their hands dirty in company? Okay. Anyways, I mean those who have done that will have this nightmare of getting a segmentation fault when the code is run. So I worked in software for some time. So this can be a big pain when you get segmentation fault. It's very big with big codes. It's a big headache. So there are some flags available in compilers. So there's an fbounds check in G-Fortran, and that is available. That I'll show you in a while. So this will check the bounds. So if well, we can show it right now. So what happens is, let's discuss it first. So in this case, if we use fbounds, so it will figure out that you had this much memory available to you, but you're trying to access something beyond that. So the compiler, this flag, will have some extra checks that are being done, and it will catch them hopefully and give you an error during compile time. Okay. In this problem, it will not happen because the variable we had passed to the subroutine, but it had no idea how long the array should be. But there is a code called segfault1.f90 that we will try now, which is where this idea will work. Let me see. So that's the end slide anyways. So let me demonstrate that to you, and then you can start working on the exercise. So we have two levels of exercises. I mean, of course, you can't finish everything today. So one is you have to try the Fortran codes available in the basic folder. Do try it out. Do read the codes. A couple of them, at least the ones we have discussed in the class. I'll put these PDFs on Moodle. Exercise 2 is more interesting. You can also take it as a homework. So you have to convert this my square root .f90 that the .py that we had written in Python into Fortran. Now you have all the information you need to write this kind of a Fortran code. Okay, so you should have again an sqrt nt function or sqrt function that we had developed using the Newton's method in Fortran, and that should I mean, you can hard code a variable equal to 2.0, let's say, and then it should be able to print the value of the square root of that variable using the Newton's method, and also compare that with the sqrt function that is available by default in Fortran. Okay, do try it out yourself. I'm sure it's easy to find solutions for it, but this is not a graded homework. You have to learn how to start writing programs. So pick a program which is closest to what you think it is. You have a basics folder now, and then or you have those programs available to you, but write the program from scratch, getting some motivation from there, and also open the Python code so that you can have an idea of what logic you are using and convert that to Fortran. So do try it out today, later today or tomorrow, and on Friday I'll try to write it in the class. Okay, so let's have a quick look at the compiler flags. In the class repository, in the Fortran/basics code, it's called segfault.f90, segfault1.f90. Okay, so let's have a look at this code. It's a very simple code. there's not even a function here. So what you're trying to do is you have an array A of size 3 that you have declared, and there's a loop going from I equal to 1 to 2000, and you're trying to set the value of A of I equal to 5. It's a classic case of the size of array is 3, so the compiler will book 3 memory locations, and then you're trying to access A of 4, A of 5. Now remember, A of 1 is the first 8 bytes, then you have A of 2 is the second 8 byte, second chunk of 8 bytes, and so on. So A of 4 will be after A of 3, but technically that should not exist. So if you try to access A of 4 equal to 5, it will try to access a memory location which is beyond A of 3. So let's run it and then see, let's compile and run it and then see what happens. So it throws a warning. It says array reference at 1, which is this one here, so A of I equal to 5, out of bounds because 2000 is greater than 3 in loop beginning at 2. So this is smart enough. I mean, if I read the warning, if I am patient enough to read warnings, I'll catch it. But this is not an error. So that means it actually generated an A dot out. So if I can actually run it, and then when you run it, in the code we are actually let me open the code as well separately, just for reference. Right. Okay. So in the code, what we are doing is we are also printing the value of I, just to catch where the error happens. So it ran till I equal to 896, although it should not have gone beyond I equal to 3, but it tried to access memory locations which are total of 893 more than what A has the size of, and then it throws a segmentation fault, invalid memory reference, and some rubbish after that. Okay. Why is this happening? So what happened was that remember I told you segmentation fault is when you try to access memory which is more than what you are allocated, and when memory allocation happens, it does not happen in only bytes, it happens in pages. This becomes something called pages of memory in a computer. So when you try to book some memory, it gave you one page or a couple of integral number of pages. So the page was of this size, and when you try to go beyond the page which was given, beyond the page size, then you actually went beyond what was allocated to you. So allocation is not equal to the number of bytes you want, it is equal to a page. So again, that is how the computers work internally. So the error happened, and it may happen that it may give a different number every time. Let's try to run it again. Yeah, this time it is a different number. Okay, so some memory could be taken by something else. So this is what is happening. So now let's try to use the f bounds check in the G-Fortran as a flag. Okay, it will compile with the warning again. Now let's try running a dot out. So now it's different. So if we compile the code with f bounds check and now we run it, it stops after I equal to 3. It says at line 11 of file segfault 1.f90 Fortran runtime error index 4 of dimension 1 of array above upper bound of 3. So this was much smarter. Okay. So compiling this with f bounds check was helpful. So if you have a big code, you have hundreds of different arrays that you're working with, and you get an error, it's worth compiling the code again with f bounds check and then see what happens. Okay. Any questions? In Python, we had something called PDB, the Python debugger. Here we have GDB. because G Fortran is GNU based compiler. So this is GNU debugger. Okay. We can also make use of that debugger here to help us out. So if I compile the code, but this time I'll use a flag called -G. So -G is a flag which compiles it with debugger support. So now if I run a.out, it runs the same way. No, it ran to some page size and crashed, but I can run it with GDB. So I can say GDB followed by a.out. So then you get a GDB prompt. Like remember, you used to have a PDB prompt. So if you run GDB followed by a.out, then you get a GDB prompt, and then now I can say run, which will actually run the code now, and then it stops, and the code is still running. I mean, it stops at 518. Now you can print the values of different variables. So let's say P of I, same as what you had in PDB. I want to see what the value of I is. It says 590. But that was not expected. I has to be, then I realized, okay, this is the problem. So you can use debugger GDB in Fortran as well. In fact, GNU based compilers. So I can use the help command, and it tells me that there are different kinds of helps available. So I want support with, let's say, help on data. I want to examine the value of data. So I can then say help data. There is lots of stuff available here, so it then gives me lots of options, and I can keep figuring out what I want, and then use that. Okay, so it's a very rich resource if you know how to use it. Okay, so it's worth trying or worth knowing about for debugging codes. I took longer than I expected, but that's all from my side today. And now you can try out things at your own pace. We don't have enough time to write the square root function, so take it as a homework. But do try all the or most of the codes that have been pushed to the repository to understand Fortran. And if you have any questions, it's worth trying it out and then asking me before just asking, because I might ask you to run it yourself and see what happens. So do question the codes and try those things out and see what happens. There is a manual available for G Fortran. So if you write man G Fortran, then it gives that you can see a lot of flags that are available in the G Fortran compiler.